Hello, everybody. So in this video, we're going to go over some questions from substitution and addition reactions. So let's start with the first question. Which of the following represents the major product of the reaction of this alkene with water under acidic conditions? So the major product will be coming from the most stable carbocation. Okay, so we have two alkenes here. So for example, for instance, if okay, if you are going to add HI, let's say, I think this is water, right? I think it's such to be water anyway. Show H. If we are going to add water onto this double bond over here, okay, then we should. We have two possibilities. One is to get the cation on the terminal carbon, or the other one is to get the cation on the on this carbon. Okay, and then the idea is if we have the cation on if you have a cation that is surrounded by more electron donating groups, more R groups, that cation will be more stable. Okay, and then this cation over here is going to have two R groups. Okay, this and this, and as a result of that, it's going to be more stable. So the more stable cation will be formed more because you have a small activation energy barrier for it to be formed. Therefore, that would be your major product. So we have two of them here. So let's consider both of them. So we have one stable cation over here. This is one, and the other one should be over here. This is going to be a tertiary carbocation. Okay. So, and as a result of that, the major product would be I and I. Okay. I think in the question they meant to say not water under acidic conditions, but HI. Okay. Anyway, I just noticed that. So anyway, the major product must be over here. So that must be our, I think, and it seems like our option C. So let's select that. Option C. Okay. Moving on to the second question. How is the rate of the substitution reaction expected to change when increasing concentration of OH minus? Okay, now this is, let's see, okay, this is a tertiary carbon over here. Okay, if you have a tertiary carbon, then it's going to undergo SN1 mechanism. Okay, if you can remember SN1 mechanism, the first step is to generate the carbocation. Okay, so here's the first step. This is going to leave. As a result of that, you're going to get the carbocation, and it does not involve OH minus. And then in the second step, you're going to have the OH minus coming in, attacking the carbocation, nucleophilic attack, generating your product, which is this. So anyway, the idea is in SN1 mechanism, the slower step is the first step because there's a bond breaking step, endothermic step. Okay, and as a result of that, and the second step is actually exothermic, so it's going to look something like that. Anyway, so because you have a high activation energy barrier for the first step, the first step will be slower, and then the rate of the entire reaction will be determined by that step. Okay, and because OH minus is not involved in that step, increasing or decreasing OH minus concentration will not affect the rate of this reaction. Therefore, you should see rate versus OH minus concentration like this. It should not change. Okay, now we're looking for this diagram in our options. Let's see if we have that. So yeah, there you go. It's option C. Moving on, third question, select the expected energy diagram for the following addition reaction. We have the acid catalyzed H3O addition. So let's go check that out. Anyway, we need to know how the addition reactions occur. Okay, there are only two ways or two mechanisms for addition reactions. One, when you add water. Okay, the other one is when you add something like HI, HCl, HBr, or HF or something like that. Okay, so for this mechanism, when you add water, okay, always let's pick up smaller alkene that is easy, which is easy to deal with. Okay, it doesn't matter because it's going to be the same case for any alkene. So in the first step, what we're going to have is we have this H3O plus, which is our catalyst getting involved, and then the nucleophilic attack will be initiated by the alkene, and we are going to break the carbon-carbon bond and then make a carbon-hydrogen bond, and then also we're going to break the hydrogen-oxygen bond in the first step. And as a result of that, you're going to get a carbocation, okay? And then we have a new CH bond added here. And in the next step, you're going to have H2O coming in as a nucleophile, and then you're going to get this cation. And then in the third step, I'm running out of space here, you're going to have a water molecule coming in and acting as a base, and it's going to grab this proton, and then it's going to break this OH bond this way, and then that will result in our product, which is this. Anyway, so you can see that we have three steps. That means there should be three humps in our energy diagram. So if we can draw them out here, okay, here's our potential energy, here's our reaction path, okay, and then in the first step we are breaking carbon-carbon bond and also HO bond and only forming CH bond. Okay, so bonds that are formed are CH and bonds that are broken are CC and HO. Because we are breaking two bonds and forming only one bond, we need to spend more energy to break the bonds. Therefore, that will be a net energy absorption. So the first step has to be an endothermic step. Okay. And the second step is forming a bond between oxygen and carbon. And then forming bonds are always exothermic. Therefore, I would say that we're going to get an exothermic step like this. And in the third step, it's an acid-base reaction. Only thing that is happening here is breaking, forming an OH bond between oxygen and hydrogen of hydrogen, and then the breaking of, okay, here's bond forming and here's bond breaking. We're forming OH bond and breaking OH bond. Therefore, it should be a thermoneutral reaction. So I would draw something like this. So anyway, this is what we're looking for in these diagrams, and let's see which option is that. Okay, so not that. Three humps. It should be overall exothermic as well. Okay, because overall we are breaking two bonds and forming two bonds, and then because we are forming two AB bonds and breaking one AA and one AB bond, there will be overall energy release. That's why the overall reaction is exothermic, and that's why we're going to select the option D. Okay, and moving on. Question 4, analyze this reaction mechanism and determine the directionality of the first step in this process. Okay, so in the first step, so when it comes to directionality, we are looking for the stable species. All right, so we can look for the acid. So in this case, we can say that it's an acid-base reaction because there's a proton transfer, right? So we can look for the stability of the acid or stability of the base. Let's go with the stability of the base first. So in the first in the first step, the base on the reactant side is this, and then on the product side, the base is this molecule over here. Now here's the thing. In both cases, we have the negative charge on oxygen, therefore feature 1 doesn't help. And when it comes to feature 2, you have a double bond, one bond away from the negative charge in our product side. Product side base, therefore it's going to be more stable due to feature 2. and therefore we can predict that this reaction is going to be product favored because most stable base is on the product side. On the other hand, if you look at the acid as well, so we have the phenol as the acid here on this side, and on the other side we have H2O as the acid. Okay, and then H2O has to be more stable than phenol. I mean, if you compare the acids as well, and that's why this reaction is going to be product favored. Okay, so anyway, so we can go with the base. The base stability for the moment. We'll do an acid question a little bit later. So this is going to be product favored because the more stable base is a product, or the weaker base is a product. Okay, so weaker base means more stable base. All right, so the correct answer is option B. Okay, and then let's think a little bit about the our acid argument. It's not relevant to this because we have already determined the answer for this question. Now, when it comes to the acid on the reactant side, you can see that you have, let me use a different color. Okay, acid on the products, and I can erase everything else as well, right? Let me erase these. Then I'm going to use, okay, here's the acid on the reactant side. Here's the acid on the product side. Okay, now if you compare these two, let's see. I mean, let's think about which acid is weaker. Okay, let's say or strong. Okay, so you can see that because in both cases, when you remove the proton, okay, here's our proton, you're going to get the negative charge on an oxygen. Therefore, which one doesn't cut it? But when it comes to the acid on the reactant side, the negative charge will be one bond away from a double bond. Therefore, that would be more stable. Therefore, the acid on the reactant side is going to be stronger. Okay, and that implies the acid on the product side is weaker. If something is weaker, that means it is less reactive. That means it is more stable. Okay, and that's why we can say that the acid on the product side is more stable as well. Okay, so it's important that we know how to use either the acid strength or the base strength to determine this, determine the favorability of the reaction or the reaction direction. Okay, and that's why I went over this exercise, even though it is not relevant to what we are doing right now. Okay, so anyway, answer for this question is option B. Let's go with that. Moving on. Question 5. Okay, question 5. Let me take another picture actually. So again, we have to pay attention to what the question is asking actually. We have to read the question carefully. The question is referring to the first step. Okay, not the overall step. So we don't have to worry about what is happening from here on out. Okay, it's not relevant. So the idea is in the first step, we are breaking in both cases, M1 and M2, we are breaking carbon-carbon and HI, and then forming these are what is broken, and then what is formed is the CH bond. Okay, and right here. Okay, no. Anyway, we are forming the CH bond. So we are forming only one bond, breaking two bonds. Therefore, we need to spend more energy to break the bonds than the energy released. Therefore, there will be a net energy absorption. Therefore, this is going to be an endothermic step. The first step will be endothermic. Now the question is, you can see that M1 and M2 have difference in the intermediate stability, right? So now the thing is, when it comes to M1, we have the carbocation formed. Let me use a different color. Carbocation formed over here, which is going to be a tertiary carbon. Okay, meaning you have 3 electron donating groups stabilizing the cation. But when it comes to M2, the carbocation is formed on this terminal carbon, okay? And for that guy, we only have one R group stabilizing, one neighbor who can stabilize this electron poor center, okay? Therefore, we know that this cation has to be more stable, which is generated by the M1 mechanism compared to M2 mechanism. If it is more stable, they should have a lower potential energy. So with M1, you should have an intermediate with a lower potential energy, and that's what we're looking for in our answers. Okay, so actually let's draw that here. So for M1, all right, so it should go it should go like this. And then when it comes to M2, actually, you know what, I should have used the other color. Let's say that, all right, so I'm going to use a different color just to be consistent with the question colors. Okay, now if here's our energy diagram, and I'm going to use red for M1. Okay, so M1 should be like this, right? And then when it comes to M2, this is M1, and when it comes to M2, I'm going to use blue, right? You're going to have a higher energy in this intermediate, or the product of the first step. Okay, so this is what we're looking for in our correct option. Okay, now let's look for that, and then that answer is not this. That was a misclick, and that must be option C. Okay, this should be our correct answer. And moving on to the next question. Select the energy diagram that corresponds to this substitution reaction. Okay, so let me take another picture. Okay, now again, this carbon is, no, I need a different color. Okay, I may use blue. Now this carbon over here is a tertiary carbon. Okay, this is a tertiary carbon containing electrophile. Whenever you have a tertiary carbon containing electrophile, because of the static hindrance and also the stability of the cation, the carbocation that is going to be formed when the living group departs, you're going to have an SN1 mechanism. Okay, meaning the carbocation will be formed before the nucleophile can get in. Okay, so as a result of that, the first step would be the formation of this carbocation, and in the next step, the OH minus will attack perform a nucleophilic attack on this carbocation to form our product, which is this. Okay, so this is two-step mechanism, and in the first step, you're going to have the generation of the carbocation, and that involves the carbocation. Okay, now the thing is, there are two steps involved, first of all. So if you draw the energy diagram for this, you need to draw two steps. Here's the potential energy, the reaction path. It should be two steps, first of all. And also, you are breaking the CBr bond and then forming the CO bond. CO bond is more polar than the CBr bond. Therefore, you are forming a stronger bond and breaking a weaker bond, meaning there should be a net energy release. Okay, because stronger bonds have a lower potential energy. You're going from a higher potential energy to a lower potential energy. Okay, so if I draw the diagram for this, then let's say this is our starting material. And in the first step, because it's a bond breaking event, it's going to be an endothermic step. Okay, and here's our intermediate carbocation. And then in the second step, it's a bond forming event. Therefore, it's going to be exothermic, and it's going to release more energy. Okay, and to make the overall reaction exothermic as well. Therefore, this is going to be our energy diagram for this reaction. Okay, so we are looking for this. Let's see which option is that. And then that option seems to be our option D. All right, moving on to question 7. What can be done to increase the amount of product at equilibrium in this reaction. So you want to increase the product, and then the only options we have are playing with the temperature and then removing or adding products or reactants. Okay, let's see. If you want to increase this, then let's think about the temperature first. This is gonna be, so this is water addition to alkene, acid catalyzed water addition to alkene. And so in this case, overall, bonds that are broken are carbon-carbon, and then HO bond of water, and bonds that are formed overall are carbon hydrogen and carbon oxygen. Because we are forming two AB bonds which are more polar, we can assume that the product side have a lower potential energy than the reactant side. Okay, therefore it's going to be overall exothermic. That means overall the products have a lower potential energy. And then if you want to favor the products which has a lower potential energy, then you need to have lower temperatures, because lower temperatures favor the state with lower potential energy. So therefore we can eliminate options A and C, okay, because we are not going to increase the temperature, we're going to decrease the temperature. And then what we want to do is, if we want to shift the equilibrium towards products, okay, then either we need to remove this product so that, you know, the product when the product concentration goes down, the reaction or the equilibrium shifts towards the products, or we can increase the concentration of the reactants like the alkene. So let's see what we have. Work at low temperatures and remove the leftover reactants. No, we cannot remove the reactants. If we remove the reactants, equilibrium will shift towards reactants, not products. So that is out. Okay, now it must be our option D. Work at low temperatures and remove the product as it forms. So that is correct. So our correct option is option D. And moving on to question 8. What is untrue about this substitution reaction? Okay, again, what we have here is a tertiary carbon that undergoes SN1 mechanism. Okay, so SN1 mechanism is going to be 2 steps always. All right, the first is the formation of the carbocation, right? And then second, the nucleophilic attack by the nucleophile. Those are the 2 steps of this mechanism. Okay, anyway, so single step is out. That is incorrect. That is untrue. Okay, it should be this. It should be 2 steps. Anyway, let's read the other ones as well. The reaction rate will double when the concentration of the electrophile is doubled. That is correct. It will likely proceed via SN1 mechanism. That is correct. An intermediate carbocation will be produced during the reaction. That is correct as well. So the correct or the untrue answer, untrue option is the first one. So so you have to select this one. Okay. Right. Selecting option A. Moving on. All right. Here's another mechanism. Let's analyze it. Analyze the mechanism for this reaction, addition reaction, and in for the rate law for this overall process. Okay, so now let's see, 2 steps, right? In the first step, let's see what is happening. We need to know the rate determining step to write the rate law. Okay, always, if you have to write the rate law, you need to know the rate determining step. Okay, and the bonds that are broken in the first step is carbon-carbon, and HI bonds are broken. And then bonds that are formed in the first step is the carbon-hydrogen bond. And then the second step or the last step is bond forming only. We are forming the carbon-iodine bond. Okay, so now if you draw the energy diagram for this, or the reaction path diagram for this, then let me draw that. Okay, The first step, we are breaking two bonds, forming only one. If we need to spend more energy to break the bond, it should be endothermic. Second step is an exothermic step because we are forming bond, right? So overall, the reaction has to be exothermic. This is always the case for this addition reaction. Addition reactions are going to be always exothermic because you are forming two AB bonds, and as a result of that, we can predict that they are going to be always exothermic. Okay, we can keep that in mind. So the energy diagram is going to look like that. You can see that we have a greater activation energy barrier for the first step and a smaller one for the second step. Now for the rate determining step must be the first step, and then the rate determining step, which is the first step, has two reactants, this alkene and HI. Now for the rate low must be rate constant times the alkene, okay, alkene times HI concentration. And that looks like our option D. All right, moving on, let's select option D and then go into next page. Here's a mechanism. You're asking to determine the energy diagram for this. Let's see if we can get three energy diagrams somehow. Okay, let's give it a shot. Now, again, yeah, when it comes to energy diagram, you need to know whether the overall reaction is exothermic or endothermic, and then you can analyze each steps as well. And then in this reaction, you can see that in the first step, let's write what is the bonds that are broken and bonds that are formed in the first step. There are three actually here. So in the first step, bonds that are broken are HBr. This is bond breaking, and bonds that are formed is bonds formed should be OH. Yeah, we're forming a stronger bond, okay, than the bond that is broken. So if you start drawing the energy diagram for this potential energy and the reaction path, the first step has to be an exothermic step because you're forming a stronger bond than the bond that is broken, okay, because OH bond is more polar than HBr bond. So I would say that it should look something like this. And then in the second step, the only thing that is happening is the breaking of a bond. You're breaking a CO bond. Bond breaking, CO, that is it. There's no bond forming in the second step. So if it is breaking, that means energy has to be provided. That means we need to supply the energy. That therefore needs to be an endothermic step. Okay, CO bond is a quite strong bond actually. Anyway, so let's say that it looks something like this. And then in the last step, we are forming a bond. We're forming a bond between carbon and bromine, and then it's not that strong compared to the bonds that we have broken before. So still, bond forming is energy releasing or exothermic. Therefore, it should be something like that. Okay, so either way, there should be three steps. First one should be exothermic. Okay, so therefore option A is out, and then B is out because there should be three steps. That means three humps. And then option C is out as well because the first step is not exothermic. Okay, so therefore only our correct answer has to be our option D. Do I have it? Okay, here you go. First step is exothermic. Okay, first step is exothermic, and then endothermic, and then exothermic. So that is correct. So we can select that as our correct answer, and that's it. We're done. And let's see how we did. Let's submit our quiz. There you go. We got 100%. Okay, I hope this helped review some of these questions from reaction mechanisms or substitution and addition reactions. And I'll see you guys in class to review more. Bye, everybody.